Welcome back, ladies and gents. In this teaching video, I'll be looking at 8.2 vector methods with projectiles. 8.2 represents chapter 8, section 2 of the Pearson A level Maths Applied Maths Year 2 textbook. I'm going to start this teaching video by going through some important facts on projectile motion. For a projectile motion, you split the motion into two equal parts, the horizontal motion and the vertical motion. For the horizontal motion, ladies and gents, we use S equal Vt. S is the horizontal displacement, V is the horizontal initial velocity, and T is the time. For the vertical motion, we use SUVAT. S is the vertical displacement, U is the vertical initial velocity, V is the vertical final velocity, A is the acceleration due to gravity, and T is the time. So over here we have a diagram. We've got a particle projected at a velocity of uxi plus uyj meters per second. This velocity vector forms an angle alpha to the horizontal. This is the pathway of the particle. It strikes the ground over here. Now, throughout the journey, the horizontal component of the velocity remains constant. It will remain as ux, as you can see over here. But the vertical component of the velocity changes. So as you can see over here, I've denoted the vertical component by v1, and over here I've denoted the vertical component by v2. Horizontal component of velocity remains constant throughout the journey. So that there are some important facts that we're going to implement within exam style questions. Here is exam style question 1. A cricket ball is hit from a point A with velocity of pi plus qj meters per second at an angle alpha above the horizontal, as you can see over here. The point A is 0.8 meters vertically above the point O, which is on the horizontal ground. The ball takes 4 seconds to travel from A to B. By modeling the ball as a particle moving freely under gravity, part A, find the value of P and Q. So, we've got a projectile question. I'm going to split the motion into two parts, horizontal and vertical. So we have horizontal. For the horizontal, I can take right to be the positive direction. Vertical. For the vertical, I can take upwards to be the positive direction. Now, for the horizontal, we use S equal Vt. So we're looking at the motion from A to B. So motion A to B. For that motion, we have that the horizontal displacement is 64. So S is 64. The horizontal initial velocity is the I component, which is P. And we multiply that by the time T, which is 4 seconds. Okay? The ball takes 4 seconds to travel from A to B. Right, so we have 64 is equal to 4P. Now we can rearrange and work out P. Okay, so P is equal to 16. Now, let's have a look at the vertical motion. For the vertical motion, ladies and gents, we use SUVAT. From A to B, the displacement is a minus 0.8. Because the ball is traveling downwards from A to B and we've taken upwards to be positive. The vertical initial velocity is the J component over here, which is Q. The velocity at which the ball hits the ground at the point B, we don't know, so we can put an X there. The acceleration is due to gravity acting downwards, so that will be minus 9.8. And the time taken for the ball to travel from A to B is 4 seconds. So the SUVAT formula that fits these quantities and helps us calculate Q would be S equal ut plus a half at squared. Okay, so I can put all of my quantities in now. So if I do that, I get minus 0.8 is equal to 4Q plus a half multiplied by minus 9.8 multiplied by 4 squared. Okay, so I can clean this up. And if I do this, I get minus 0.8 is equal to 4Q minus 78.4. Okay, so I can make Q the subject, simply rearrange and we get Q. So if I do this, I get Q is equal to 19.4. So we've got the value of P and we've got the value of Q. That there, ladies and gents, completes part A of the question. Moving on to part B of the question. Find the initial speed of the ball. So the initial speed can be written as a vector. We'll call that vector U squiggle. So U squiggle is equal to Pi plus Qj. We've calculated P and Q. P was 16, Q is 19.4. So U squiggle is equal to 16I plus 19.4J. To find the speed, we take the magnitude of this particular vector. So the magnitude of this vector is equal to square root 16 squared plus 19.4 squared. Okay, so I can put this into my calculator and I get the following result. 25.1 meters per second to 3 significant figures. Okay, so for part B, the initial speed of the ball is 25.1 meters per second. Moving on to part C. Find the exact value of tan alpha. Well, over here I can construct a right angle triangle. So my right angle triangle looks something like this. The opposite will just be the J component, that is Q, and Q is 19.4. The adjacent will be the I component, which is P. P is 16. So we have that tan alpha is equal to opposite of adjacent, 19.4 over 16. So we can put this into our calculator and we end up with tan alpha is equal to 97 over 80. So that there, ladies and gents, is the exact value of tan alpha. Let's have a look at part D of the question. Find the length of time for which the cricket ball is at least 5 meters above the ground. Let's label 5 meters above the ground. So we could have it over here, for example. Since the quadratic curve is symmetrical, it could also be labeled over here. This point over here, suppose the time is t1, and this point over here, suppose the time is t2. We want to find the length of time for which the cricket ball is at least 5 meters above the ground. During this pathway, the cricket ball is at least 5 meters above the ground. The duration will just be t2, take away t1. Right, so I'm going to work out the value of t1 and the value of t2. For simplicity, let's just look at the vertical motion. So vertical, take upwards to be the positive direction. We can write SUVAT. So the vertical displacement from here to here will technically be 5 take away 0.8, and that is 4.2. It's positive because we're taking upwards to be the positive direction, and the displacement over here is upwards. Right, the vertical initial velocity will be the J component, which is 19.4. The vertical final velocity we don't know. The acceleration is due to gravity, and that will be minus 9.8. And we're trying to work out the time. So the SUVAT formula that fits this is S equal ut plus a half at squared. So we have S equal ut plus a half at squared. Let's put all the values in. This gives us 4.2 is equal to 19.4t plus a half multiplied by minus 9.8 t squared. Let's clean this up. We get 4.2 is equal to 19.4t minus 4.9t squared. Take everything to one side. This gives us 4.9t squared minus 19.4t plus 4.2 equal to 0. This is a quadratic equation. We can solve it to work out the two possible values for t. So, using our ClassWiz calculator, the two possible values of t would be 0.230 and 3.73. So each of these are given to 3 significant figures. Okay, now what is my t1? Well, my t1 is my 0.230. The t2, will therefore be 3.73. Now we can work out T2 minus T1, the length of time for which the cricket ball is at least 5 meters above the ground. Okay, so we have T2 minus T1 is equal to 3.73, take away 0.23, 0. This gives us 3.5 seconds. So the length of time for which the cricket ball is at least 5 meters above the ground would be 3.5 seconds. The final part of the question is part E. State an additional physical factor which may be taken into account in a refinement of the above model to make it realistic. So for example, we could take the weight of the ball. Consider the weight of the ball. We could also consider air resistance. So these two physical factors may be taken into account as a refinement of the above model. That there, ladies and gents, completes exam style question 1. Let's have a look at exam style question 2. A particle P is projected with velocity 3u(i) plus 4uj meters per second from a fixed point O on horizontal ground. Given that P strikes the ground at a point 750 meters from O, part A show that u is equal to 17.5. First of all, I'm going to draw a diagram to model this situation. We have a horizontal ground. Here is the point O. This is my particle. It is projected at a velocity of 3u(i) plus 4uj meters per second. Okay, so this is the pathway of the particle. It's going to strike the ground over here. Let's call that point A. A is 750 meters from O. So we have 750 meters from O. The acceleration due to gravity, we can label it acts vertically downwards, g meters per second. So in part A, we want to show that u is equal to 17.5. Let's split the motion into horizontal and vertical. So we've got horizontal. Let's take right to be the positive direction. Vertical. Let's take upwards to be the positive direction. So horizontally, we use S equal Vt. The horizontal displacement from O to A is 750. So we've got 750 equal to the horizontal initial velocity is the I component, which is 3u. The time taken for the particle to move from O to A is unknown, so we can keep it as t. Now over here, I can make t the subject, so if I do this, I get the following result. T is equal to 250 over u. Okay, so that t equal to 250 over u, I can call it equation 1. Let's move on to the vertical motion. So for the vertical motion, we have SUVAT. I can write SUVAT. The vertical displacement from O to A is 0. The particle starts at the ground, comes back to the ground. Vertical displacement is 0. The vertical initial velocity is the j component, that is 4u. The vertical final velocity, so the velocity at which the particle strikes the ground at the point A, is unknown, so we can just put an X there. A is equal to minus 9.8, and t, we can just make it equal to itself, t. So now the SUVAT formula that we can use that fits this is S equal ut plus a half at squared. So we have S equal ut plus a half at squared. Let's substitute the values in. 0 equal to 4ut plus a half multiplied by minus 9.8 t squared. Cleaning this up gives us 0 is equal to 4ut minus 4.9 t squared. That there's equation number 2. Now we can substitute equation 1 into equation 2 to eliminate the t's, hence we'll get an equation involving u. Then we solve for u to show that u is equal to 17.5. So let's substitute equation 1 into equation 2. Doing this gives me a 0 is equal to 4u multiplied by 250 over u minus 4.9 multiplied by 250 over u whole squared. Notice that the u's over here cancel out and we have to square this bracket. So if I simplify this particular equation, I end up with the following result. 0 is equal 1000 minus 306250 over u squared. So now I can make u squared the subject. So if I do this, I get u squared is equal to 306.25. We're nearly there. We take the square root. We're going to take the positive square root because upwards is the positive direction and that particular u is acting in the upwards direction. So we can take the positive square root of 306.25. And if we do this, we end up with 17.5 exactly. So that there, ladies and gents, is the end of part A of this exam style question. Moving on to part B. Calculate the greatest height above the ground reached by P. So the greatest height is over here. I'm going to modify my diagram. Okay, so here's my modification. Okay, right, so let's call this point over here point A. So the particle starts at the origin O, travels, reaches its greatest height at the point A. This greatest height we don't know, we can call it y. And the horizontal displacement, we can call it x. We have acceleration due to gravity acting vertically downwards, and we know that u is equal to 17.5. I can substitute it into here and get my vector in numerical form. So if I do that, I get the following. 3 times 17.5 is 52.5. So we have 52.5i. 4 times 17.5 is 70. So we have 70j. So that there is my vector in numerical form. Now what is my target? Well, I want to work out the greatest height above the ground reached by P. So the target is to work out y. So how do we calculate y? As a standard procedure, let's split the motion into horizontal and vertical. So horizontal, take right to be positive. Vertical, take upwards to be positive. Horizontally, we have S equal Vt. And vertically, we have SUVAT. Let's have a look at the horizontal motion. Now, the horizontal displacement from O to A is just x equal. The horizontal initial velocity is the I component, which is 52.5. And the time taken from O to A, so that there's the greatest height, we don't know, so we can just keep it as t. Does this help us calculate y? It does not, so let's move on to the vertical motion. So the vertical displacement from O to A is my y. The vertical initial velocity is the j component, centi. At this greatest height, the particle is stationary, so the final velocity from O to A is 0. Final vertical velocity. A is minus 9.8. And the t we don't know. Okay, we don't know the time taken from O to A. So we can just leave it as t. Alternatively, you can just put an x, but let's just leave it as t. Now the SUVAT formula that fits this, that helps us calculate y, is v squared equal u squared plus 2as. So let's put all the numbers in. We have 0 squared is equal to 70 squared plus 2 lots of the acceleration minus 9.8 multiplied by s, which is y. Okay, so if I clean this up, I get the following result. 0 is equal to 4,900 minus 19.6 y. So now we can make y the subject, and if we do this, we get y equal to 250 meters. Hence, the greatest height above the ground reached by P is 250 meters. Here is the final part of the question. Part C, find the angle the direction of motion of P makes with I when t is equal to 5. So we're trying to work out the angle between the velocity vector when t is equal 5 and the vector I. Why is there the angle between the velocity vector when t is equal 5 and the vector I? Well, it says direction of motion, so movement. So we're looking at the velocity vector when t is equal 5, and we want the angle between this velocity vector and the vector I. Okay, so if we go back to our diagram, this whole distance here, the horizontal displacement from O to the point A where the particle strikes the ground, is 750. 750 divided by 2 is 375 meters. So half the distance is 375 meters. Up until this point over here. Right. That there is important to us. I'll explain later on. Let's split the motion into horizontal and vertical. So we have horizontal. Take right to be positive, for example. Vertical. Take up to be positive. Right, for the horizontal motion, we use S equal Vt. And for the vertical motion, we use SUVAT. So SUVAT. Anyways, let's go back to the horizontal motion. The horizontal displacement when the particle has traveled for 5 seconds, we don't know, we can call that x. So x equal. The horizontal initial velocity is 52.5. And we multiply this by time t equal 5. Okay, so we can put this into our calculator and we get x equal 262.5 meters. So after t equal 5 seconds, the horizontal displacement is 262.5 meters, which is actually less than 375 meters. So now I'm going to modify this diagram so that we have restricted the diagram up until t equal 5 seconds. So we can delete this whole part over here. That there's halfway through, but the horizontal displacement for halfway through was 375 meters. So we delete more of this diagram and we end up somewhere over here. Okay, so that horizontal displacement is 262.5 meters. So the particle is there at that point where t is equal 5. Right, remember the horizontal velocity is constant throughout the journey. So that horizontal velocity will be constant and it will be 52.5. What I want to do is work out the vertical component. This is my overall velocity. What is that vertical component at time t equal 5? This is where we have to look at the vertical motion. So we've got SUVAT. Let's fill in the blanks. The vertical displacement from this point to this point, we don't know, so we can put an X there. The vertical initial velocity is the J component, 70. The vertical final velocity at time t equal 5, question mark, we're trying to calculate that component. The acceleration is minus 9.8 and the time t is equal 5. So now we can use an appropriate SUVAT formula to work out v, and that would be v equal u plus a t. Let's put all the values in. So we have v equal 70 plus minus 9.8 multiplied by t, which is 5. Okay, so I can put this into my calculator and I get v equal 21 meters per second. So this component over here, the vertical component of the velocity vector at time t equal 5 is 21. Let's write down the vector for the velocity when time t is equal 5. That would be 52.5 I plus 21 j meters per second. If I wanted to work out the speed of the particle after t equal 5 seconds, I just take the magnitude of this velocity vector. Anyways, what I'm trying to work out is the angle between the velocity vector when t is equal 5 and the vector I. Let's represent this on a coordinate grid. So here's my coordinate grid. This is the I-axis, this is the j-axis. So 52.5 I plus 21 j will look something like this. So we have 52.5 I plus 21 j. Now we want the angle between this velocity vector and the vector I. So we're trying to calculate this angle x. So if I form a right angle triangle, this length over here is 21 and this length over here is 52.5. To work out x, I can use trigonometry. Tan x is equal to opposite over adjacent. So x is equal tan inverse of my fraction. We can put this into our calculator and we can round to 3 significant figures and we get x equal 22 degrees. So the angle, the direction of motion of P makes with I when t is equal 5 is 22 degrees. Suppose the question was find the angle the direction of motion of P makes with J when t is equal 5. So that angle would therefore then be this angle here. To work out that angle, we simply do a 90 minus x, so 90 minus 22, which is 68 degrees. So the angle, the direction of motion of P makes with J when t is equal 5 will therefore be 68 degrees. 90 minus 22 is 68 degrees. But that there wasn't relevant to the question, but I thought I'll go through it to give you a deep understanding of what's going on. Okay, that there, ladies and gents, completes part C of the question and this exam style question. If you found this video useful, please don't forget to leave a comment, leave a like, turn on the notification bell so that you get notifications every time I upload a video, and please don't forget to subscribe.